Picture a star not as we know it, a brilliant point of light in the night sky, but as something entirely different. Imagine it cloaked in an immense, geometric structure, a vast artificial shell harvesting its energy so completely that it flickers like a signal to the universe. This is the Dyson Sphere, a megastructure so colossal it defies everything we understand about engineering, ambition, and perhaps even life itself, and the most thrilling possibility. We might not be the ones building it. What if these cosmic wonders already exist out there, crafted by civilizations far beyond our own? The idea of a Dyson Sphere isn't just science fiction, it's a serious scientific concept, a beacon that could mark the presence of a civilization mastering energy on a scale we can barely fathom. Think about it, a society advanced enough to dismantle planets, reshape solar systems, and harness the raw power of a star. What would that mean for us staring up at the sky, searching for signs of intelligence beyond Earth? Could these structures be the ultimate clue, hiding in plain sight, waiting to rewrite our place in the cosmos? That's exactly what we're about to explore: the science, the mysteries, and the mind-bending possibilities of Dyson Spheres. We'll dive into how they might work, why they could be the key to finding advanced alien life, and what it would mean if we actually detected one. From the visionary mind of physicist Freeman Dyson to the cutting-edge telescopes scanning the stars for anomalies, this journey will take us to the edge of human imagination and beyond. So buckle up, by the end of this you might never look at the night sky the same way again. Freeman Dyson didn't just imagine a structure, he redefined what a civilization could become. His concept, now known as the Dyson Sphere, isn't a single rigid shell like some sci-fi depictions suggest. Instead, think of it as a swarm of millions or even billions of energy-capturing satellites orbiting a star, each one angled to soak up sunlight and beam it back for use. Picture a hive of solar panels, but on a scale so vast it could eclipse the star itself. The goal: to capture every drop of energy a star produces, something like the output of our sun, but harnessed entirely. Now let's talk about scale. Our largest human-made structures, skyscrapers, dams, even the Great Wall of China, are microscopic compared to a Dyson Sphere. These megastructures would span distances measured in astronomical units, meaning they'd stretch farther than Earth's orbit around the sun. Constructing something like that would require materials we can barely dream of today. Imagine dismantling whole planets, converting their mass into solar collectors, or even mining asteroids for resources on an industrial scale never attempted. The materials alone boggle the mind. A Dyson Sphere wouldn't be built from steel or concrete. It'd need something far lighter, stronger, and heat-resistant, perhaps nanomaterials or self-repairing alloys. Heat dissipation would be another nightmare. Even capturing a fraction of a star's energy would generate temperatures beyond anything our current tech could handle. And then there's stability, keeping all those components in perfect orbit without collisions or gravitational chaos. But here's the fascinating twist: the Dyson Sphere isn't just about energy. It's a signature. A civilization capable of building one would have moved beyond planet-bound life, mastering space travel, mega-engineering, and resource management on an interstellar level. That's why scientists search for these structures not just as power plants, but as cosmic breadcrumbs leading us to intelligence far beyond our own. If we ever spot strange dimming around a star or unusual heat signatures where none should exist, we might be staring at the ultimate evidence that we're not alone. Capturing the energy of an entire star might sound impossible, but the physics behind it is surprisingly straightforward if you have the right technology. A Dyson Sphere works by intercepting the star's radiation before it escapes into space, converting that raw stellar power into usable energy. Think of it like wrapping a star in a solar panel, except instead of just catching sunlight like we do on Earth, this structure would absorb every single photon the star emits. The energy output would be staggering. Our sun alone releases enough power in 1 second to meet human energy demands for nearly 1 million years. Now, thermodynamics introduces some serious challenges. One of the biggest is heat. A functioning Dyson sphere can't just absorb energy, it needs to radiate the excess heat away or the whole structure would melt. That means engineers would have to design it to balance absorption with infrared emissions, creating a thermal equilibrium that doesn't cook the system. Some theories suggest using special materials that can handle extreme temperatures, while others propose an open swarm design that allows heat to dissipate naturally into space. Gravitational forces add another layer of complexity. A solid shell around a star would experience crushing gravitational stress, constantly pulled inward while resisting the star's immense gravity. That's why most realistic designs propose a Dyson Swarm, millions of independent satellites orbiting in harmony rather than a single rigid structure. Each collector would need precise orbital adjustments to avoid collisions while maintaining optimal energy capture. Even then, stabilizing such a massive system would require advanced propulsion or even artificial intelligence to manage the constant micro-adjustments needed. Material science is the final hurdle. Building something on this scale means rethinking construction from the ground up. Traditional metals would fail under the heat and stress, so futuristic materials like carbon nanotubes or graphene might be necessary, lightweight yet incredibly strong. Self-repairing mechanisms would be crucial, as even tiny fractures could cascade into catastrophic failures. And then there's the sheer quantity of material required. Some estimates suggest dismantling entire planets just to gather enough resources. But here's the intriguing part. Despite these challenges, nothing in our current understanding of physics outright forbids a Dyson sphere. The obstacles are immense but not insurmountable for a civilization with enough time, resources, and motivation. That's why astronomers keep searching. If we ever spot a star with unusual dimming patterns or excess infrared radiation, we might be looking at a megastructure built by minds far more advanced than our own. Freeman Dyson's groundbreaking idea didn't emerge in a vacuum. It was born at the intersection of hard science and wild imagination. In 1960, he published a one-page paper titled "Search for Artificial Stellar Sources of Infrared Radiation," and with it, he reshaped how we think about advanced civilizations. What's fascinating is that Dyson wasn't proposing a blueprint for construction. Instead, he framed it as a detection strategy. If alien societies existed, they'd need vast amounts of energy, and their engineering might betray their presence through unusual heat signatures in space. Dyson drew inspiration from an unlikely source: science fiction. He openly credited Olaf Stapledon's novel Star Maker, which described civilizations enveloping stars to harness their power. But Dyson did something revolutionary. He took that fantastical concept and anchored it in real physics. His vision wasn't about solid shells, an idea popularized later by fiction, but about swarms of orbiting collectors, a design far more plausible given the gravitational and material constraints. This nuance is key. Dyson wasn't dreaming up a megastructure for humans to build. He was giving astronomers a roadmap to find others who might have already done it. The scientific community initially met his paper with skepticism. After all, searching for alien megastructures sounded like the plot of a pulp novel, not rigorous astrophysics. But Dyson's brilliance lay in his framing. He argued that even if the idea seemed outlandish, the tools to test it already existed. Infrared telescopes could, in theory, spot the waste heat from such structures, a practical, observational approach rather than pure speculation. Slowly, his peers began to see the merit. What started as a thought experiment evolved into a legitimate field of study, influencing projects like SETI and modern exoplanet research. Dyson's legacy here isn't just the sphere itself, it's the shift in perspective he triggered. By daring to ask how unfathomably advanced civilizations might operate, he expanded the boundaries of astrobiology and engineering. Today, when astronomers analyze strange stellar dimming or anomalous infrared emissions, they're walking the path Dyson laid down over half a century ago. His idea reminds us that sometimes the most profound scientific leaps begin not with equations, but with a simple question. If they're out there, what would we see? The concept of a Dyson sphere isn't one size fits all. It's a spectrum of megastructures, each with its own wild engineering quirks and cosmic implications. Let's start with the most plausible design, the Dyson Swarm. Picture this: not a single solid shell, but millions or even billions of individual energy collectors orbiting a star in coordinated harmony. Think of it like a hive of giant solar panels, each one angled to catch sunlight and beam it back to a central hub. The advantage: flexibility. A swarm could be built incrementally, one satellite at a time, scaling up as a civilization's needs grow. Collisions could be managed with precision orbits, and repairs would only require fixing individual units rather than an entire structure. But here's the catch: coordinating that many moving parts would demand insane levels of computational power and energy management, like conducting a symphony where every instrument is a continent-sized power plant. Then there's the Dyson bubble, a twist so clever it borders on sci-fi magic. Instead of orbiting, these structures would hover in place using light pressure. How? Imagine massive, ultra-thin mirrors or solar sails balancing the star's radiation pressure against its gravity, essentially floating in a static position. These statites wouldn't need complex orbital mechanics, eliminating collision risks. The trade-off: material science becomes the bottleneck. The statites would need to be impossibly lightweight yet durable enough to withstand stellar winds and radiation for centuries. Even a tiny tear could send one careening into the star, and while a bubble might be easier to stabilize than a swarm, building it would require technology so advanced it might as well be alien to us today. Now the classic image, the Dyson shell. This is the one that fires up our imaginations, a solid, rigid sphere encasing the entire star like a cosmic snow globe. The appeal is obvious: total energy capture, no gaps, no wasted photons, but the challenges, they're astronomical. A solid shell would experience unimaginable gravitational stress, straining to avoid collapsing into the star. And then there's heat. Without a way to radiate excess energy, the interior would become a furnace, cooking the structure itself. Some theorists suggest a partially completed shell or one with vents, but even then, the engineering hurdles are so vast, it's hard to see how any civilization could pull it off without bending the laws of physics as we know them. So why do these variations matter? Because each one leaves a different fingerprint on the cosmos. A swarm might cause subtle, irregular dimming as its components pass in front of their star. A bubble could emit unusual infrared patterns from its hovering mirrors, and a shell, if one exists, it might blot out its star almost entirely, glowing faintly with waste heat. These aren't just engineering exercises, they're blueprints for detection. When astronomers scan the skies for anomalies, they're not just looking for a Dyson sphere. They're hunting for clues that reveal which type a civilization might have chosen, and what that choice says about their technological prowess. After all, the kind of structure you build isn't just about energy. It's a statement, a declaration of how far a species has come in its quest to master the universe itself. Could humanity actually build a Dyson sphere today? The short answer: no, not even close, but the long answer reveals just how far we'd need to leap and what that staggering journey might look like. Right now, our most ambitious space projects involve landing robots on Mars and maintaining a small orbital station. Compare that to dismantling planets, constructing megastructures across solar systems, and harnessing stellar energy. It's like comparing a child's sandcastle to the Great Pyramid. Take materials alone. Even if we redirected every ounce of steel, concrete, and carbon fiber on Earth toward construction, we'd barely scratch the surface. A single Dyson swarm might require more material than exists in our entire inner solar system. That means asteroid mining on an unimaginable scale, not just grabbing a few space rocks, but systematically disassembling Mercury, Venus, or even Mars. The logistics are nightmarish. Transporting that much mass would require propulsion systems we've only dreamed of, like antimatter engines or solar sails the size of continents. And then there's fabrication, building in orbit or in deep space, likely using self-replicating robots, since human hands couldn't possibly assemble trillions of components. Energy is another impossible hurdle. Ironically, we'd need colossal power just to begin construction power we don't yet have. Current global energy production is a drop in the bucket compared to what mega engineering demands. Some theories suggest bootstrapping with fusion reactors or orbital solar arrays, but even those would take centuries to scale up, and time is the cruelest factor. Even if we started today with unlimited funding and global cooperation, conservative estimates suggest a Dyson swarm might take 10,000 years to complete. That's longer than all recorded human history. Then there's the ethical quagmire. Who gets to control a star's energy? Would this become a tool for inequality, monopolized by a single nation or corporation? Or could it unite humanity under a common project, like a modern-day Apollo program, but lasting millennia? And what happens to Earth if we strip neighboring planets for parts? The ecological and geopolitical ripple effects could be catastrophic long before the first solar collector goes online. But here's the twist: our inability to build one today doesn't make the concept worthless. The pursuit forces us to confront our limits and imagine solutions. Maybe we'll discover radical new physics like room temperature superconductors or stable wormholes that rewrite the rules. Or perhaps future AIs will engineer workarounds we can't yet fathom. The Dyson Sphere isn't just a structure, it's a mirror reflecting both our audacity and our humility. For now, it remains a beacon in the dark, guiding our aspirations toward horizons we're only beginning to glimpse. The Fermi paradox hangs over astronomy like a riddle wrapped in silence. Billions of stars, countless planets, and yet no signals, no visits, no trace of civilizations beyond our own. Where is everybody? Physicist Enrico Fermi famously asked. Dyson spheres might hold the answer, or they could make the mystery even stranger. Consider this: if advanced civilizations exist, they'd need mind-boggling amounts of energy. A Dyson sphere isn't just a power plant, it's a logical endpoint for any society pushing the limits of growth. So why haven't we spotted one? One possibility is thrilling: we might not be looking hard enough. Stars with unusual dimming or excess infrared heat could be hidden megastructures camouflaged as natural phenomena. The infamous Tabby star, which dims erratically, sparked exactly this debate. Some argued for swarms of orbiting collectors, while others pointed to cosmic dust. The truth remains elusive, but the hunt itself reveals how Dyson spheres could solve Fermi's paradox. If they're out there, hidden in plain sight, the universe might be louder than we think, just in ways we're only beginning to decode. But there's a darker alternative. What if the silence means Dyson spheres are gravestones? A civilization capable of building one has mastered its star, but that level of control might come with existential risks. Imagine a society so advanced it becomes dependent on a fragile, planet-sized machine. One catastrophic failure, a collision in the swarm, a material flaw, could trigger collapse. The same engineering prowess that lets a species harness a star might also pave the way for its downfall. If that's true, the absence of contact isn't a sign we're alone. It's a warning that the greatest achievements might carry the seeds of self-destruction. Then there's the unsettling third option: we're looking at the puzzle backward. Maybe Dyson Spheres aren't rare because civilizations fail. Maybe they're rare because truly advanced societies transcend them. A culture millions of years ahead of us might have moved beyond megastructures entirely, tapping into energy sources we can't yet conceive. Dark matter reactors, quantum vacuum energy. If that's the case, the paradox deepens. The universe could be teeming with life so advanced, it's invisible to our telescopes, operating on principles that make Dyson Spheres look like steam engines. This isn't just speculation, it reshapes how we search. If we limit ourselves to hunting for star-encircling hardware, we might miss subtler evidence. Unusual energy signatures, patterns in cosmic background radiation, even anomalies in gravitational waves could point to technologies beyond our current imagination. The Fermi paradox forces us to confront not just the silence, but our assumptions about what noise should sound like. Dyson Spheres might be the first clue, the last gasp, or a stepping stone to something even more extraordinary. Either way, their absence speaks volumes. The question isn't just where is everybody, it's what are we missing? Dyson Spheres might be invisible to the naked eye, but they'd leave a glaring fingerprint in the infrared spectrum, one our telescopes are already equipped to spot. Here's why: every energy system leaks waste heat, and a megastructure swallowing a star's light would re-emit that energy as infrared radiation. Picture a giant radiator in space, glowing at temperatures we'd expect from something room temperature on Earth, but on a cosmic scale. That's the telltale signature astronomers hunt for, not the sphere itself, but the heat it can't hide. NASA, a wise telescope designed to map the sky in infrared, has already scanned millions of objects for exactly this kind of anomaly. Most stars follow predictable thermal patterns, but a Dyson sphere would stand out like a bonfire in a snowstorm. Instead of emitting most of its energy as visible light, the star would appear oddly dim in our telescopes while blasting infrared, a mismatch that screams artificial. In fact, researchers have already flagged candidates. Take, for example, a star catalogued as WISE 0855-0714, a bizarre object emitting almost no visible light but radiating intense infrared. Could it be a failed star or something far more intriguing? The data keeps astronomers guessing. Future missions like the James Webb Space Telescope or the proposed Louvre Observatory could take this search to the next level. With unprecedented sensitivity to infrared wavelengths, they might detect subtler signs. Partial Dyson swarms under construction, or megastructures so efficient their waste heat is minimal. Even more exciting are the anomalies we haven't predicted. A civilization advanced enough to build a Dyson sphere might tweak its design in ways that produce unexpected thermal patterns, perhaps directional emissions to power interstellar travel, or heat sinks disguised as natural cosmic phenomena. But the challenge isn't just sensitivity, it's ruling out false positives. Cosmic dust clouds, young stellar nurseries, and even rogue planets can mimic infrared excess. That's why detection requires more than a single odd reading. Scientists look for recurring anomalies like stars that dim erratically while their infrared glow remains steady. It's a cosmic game of elimination, where every candidate gets scrutinized for natural explanations before whispers of alien megastructure even enter the conversation. The beauty of this approach is its universality. Unlike radio signals, which a civilization might choose to broadcast or hide, infrared leakage would be nearly impossible to fully suppress. Waste heat is physics' way of keeping score. Even the most advanced builders couldn't erase it entirely. So while we might never see a Dyson sphere directly, its thermal ghost could linger in our telescope's data, waiting for the right algorithm, the sharp-eyed researcher, or the next-generation observatory to finally say, there. That's not a star, that's someone's masterpiece. KIC 846285-2, better known as Tabby's star, might sound like just another catalog entry, but this flickering oddball in the constellation Cygnus sparked one of the most electrifying debates in modern astronomy. At first glance, the star seems ordinary, but its light curves tell a different story. Mysterious, erratic dimming events where its brightness drops by up to 22% in ways no natural phenomenon should. The pattern was so bizarre that when astronomer Tabby and her team published their findings in 2015, the internet erupted with whispers of aliens. Could this be it, the first hard evidence of a Dyson sphere under construction, its swarm of collectors blotting out the star's light as they passed? The initial excitement wasn't just hype. Natural causes struggled to explain the data. Planets, even giant ones, typically cause predictable, periodic dips in starlight as they orbit, but Tabby's star dimmed unevenly, sometimes for days, sometimes weeks, with no rhythm. Dust clouds, young stars often have messy debris disks, but Tabby's star isn't young. Its spectrum shows no excess infrared, ruling out warm dust that should glow if it were blocking that much light. The anomalies defied textbook explanations, leaving room for something extraordinary. Enter the alien megastructure hypothesis. The idea wasn't that a full Dyson sphere eclipsed the star, but perhaps a partially built swarm, a colossal construction site in space. Imagine a civilization assembling its first few million collectors, their orbits still chaotic, creating irregular shadows. It was a tantalizing thought, one that even skeptics had to entertain because scientifically, you can't dismiss a theory without evidence. For a brief, thrilling moment, humanity stared at the data and wondered, are we seeing the handiwork of engineers who aren't human, but science thrives on doubt? As more eyes turned to Tabby's star, alternative explanations emerged. Detailed studies suggested swarms of cold, diffused dust likely from shattered comets or colliding moons could explain the dimming without invoking aliens. These particles would be too chilly to emit detectable infrared, sidestepping earlier objections. Even more convincing, further observations caught the star dimming more in blue light than red, a hallmark of scattered starlight, exactly what you'd expect from fine dust grains. The plot thickened when researchers noticed the dimming grew less extreme over time, as if the dust were dispersing or falling into the star, yet the mystery isn't fully solved. Why would a mature star like this have so much dust? Some propose a recent planetary collision, a cosmic catastrophe littering the system with debris. Others speculate about a rare, massive ringed planet, its uneven structures casting intricate shadows. Each theory has gaps, keeping the door slightly ajar for those still dreaming of megastructures. But here's the real lesson. Tabby's star didn't just challenge our assumptions, it revealed how unprepared we are to recognize truly alien engineering. The disappointment some felt when natural explanations gained traction misses the bigger picture. Whether it's dust or Dyson, Tabby's star proved something profound. Our tools can detect anomalies that push the boundaries of known physics. The next time we spot a star acting strangely, we'll be ready not just to ask could it be aliens, but how do we prove it isn't? That shift from speculation to rigorous detection is the true legacy of this cosmic riddle. One day, we might find a star where all natural explanations fail, and when that happens, we'll owe part of the discovery to the curious case of Tabby's star. Tabby's star isn't the only cosmic oddball raising eyebrows. The universe is full of stellar mysteries, and a handful of them glow just a little too strangely in infrared, enough to make scientists lean in and ask what's going on here. Take Epoch 204278916, a young star in the Scorpius constellation. When astronomers observed it in 2016, they caught something bizarre. Its light dimmed by up to 65% in erratic bursts, far deeper than any known planet could cause. Even weirder, the dips weren't symmetrical. Some lasted days, others mere hours, like a cosmic strobe light flickering without rhythm. Theories exploded. Was it a warped protoplanetary disk, a swarm of colossal comets, or something more deliberate? Then there's VVVWIT-07, a giant star in the Milky Way that suddenly faded by 97%, nearly vanishing before slowly brightening again over 200 days. Stars this massive don't just dim casually, they're luminous powerhouses. Yet here was one playing peekaboo with the cosmos, the best natural explanation. An enormous dust cloud, possibly from a companion star or a shattered planet. But the scale was mind-bending. Whatever blocked the light had to stretch billions of miles, dwarfing anything in our solar system. Could it be a failed Dyson Swarm, a mega-project abandoned mid-construction, leaving behind a haze of debris? The challenge with these candidates isn't just spotting anomalies, it's resisting the allure of jumping to cosmic conclusions. For every tantalizing what if, there's a mundane but equally fascinating natural answer. Epoch 204278916's odd behavior might trace back to a monstrously large ringed planet, its uneven edges casting jagged shadows. VVVWIT07's dimming could stem from a rare stellar tantrum, ejecting enough dust to shroud itself temporarily. Even natural explanations push the boundaries of what we thought stars could do, revealing how much we still don't understand about the universe's ordinary chaos. That's why astronomers tread carefully. The hunt for Dyson Spheres isn't about labeling every oddity as alien. It's about sifting through the noise for the one signal that defies all natural explanations. Each candidate star is a puzzle, and the process of elimination is just as thrilling as the prospect of discovery. Because here's the thing. If we ever find a star where every natural hypothesis falls short, where the data points irrevocably toward artificiality, it won't be because we jumped at the first strange flicker. It'll be because we ruled out everything else, leaving only the impossible as the answer. And that's when the real conversation begins. Imagine a computer so vast it makes a Dyson sphere look quaint. A celestial supermachine wrapped in layers around a star, each level humming with computation at scales beyond human comprehension. This is the Matrioshka Brain, a hypothetical megastructure that takes the idea of stellar engineering to its ultimate extreme. While a Dyson sphere captures a star's energy for power, a Matrioshka Brain uses that energy to think. Picture concentric shells of computing substrates, each one radiating waste heat inward to the next, forming an unfathomable neural network powered by starlight itself. The name comes from Russian nesting dolls Matryoshka because each layer nestles inside the other, turning thermodynamics into a computational symphony. The implications are staggering. A civilization that builds a Matryoshka brain isn't just harnessing energy, it's transcending biology. Think about it. Why limit intelligence to fragile, carbon-based life forms when you can upload consciousness into a star-powered mainframe? Such a structure could host simulations of entire universes, solve problems in seconds that would take humanity millennia, or even simulate every possible permutation of its creator's history. This isn't just a computer, it's a godlike engine of thought capable of running ancestor simulations so detailed they'd be indistinguishable from reality. Some theorists argue that if post-biological life exists, this is how it would manifest not as little green men, but as silent, swirling layers of machinery turning stars into servers. But here's the twist. A Matryoshka brain might be less visible than a Dyson sphere. While a classic Dyson swarm leaks detectable infrared, an optimized brain could recycle waste heat so efficiently it'd barely radiate anything at all. Every joule of energy would be squeezed for computation, leaving little to escape into space. That raises a haunting question. Could these cosmic superminds already exist, hidden in plain sight, their presence masked by their own perfection? If so, our search for alien life might be like ants scanning the sky for other ants, oblivious to the supercomputers towering over us. The ethics of such a structure are just as mind-bending as the engineering. What would a civilization do with that much computational power? Run utopian simulations, solve entropy itself, or perhaps freeze itself in infinite loops of pleasure, lost in a digital nirvana. There's a dark edge too. A species that uploads itself into a Matrioshka brain might abandon the physical universe entirely, retreating into curated realities while the cosmos outside grows cold and silent. It's a sobering thought. The pinnacle of intelligence might not reach outward but inward, turning stars into escapism. Yet for all its grandeur, the Matrioshka brain is still rooted in physics we almost understand. The energy is there. The materials, while ludicrously advanced, don't violate known laws. Even the concept of nested heat recycling mirrors how Earth's own ecosystems waste nothing. The real barrier isn't feasibility at scale. Building one would require mastery over self-replicating nanotech, precision gravity manipulation, and energy systems that make fusion look like a campfire. But for a civilization thousands or millions of years ahead of us, it might just be the next logical step. So while we sift through telescope data for Dyson Spheres, we should remember, the universe's most advanced minds might not be signaling us with megastructures. They might be too busy thinking, and if we ever stumble upon a star that's too quiet, its light a little too dim, its heat suspiciously absent, we might not be staring at an abandoned project. We might be looking at something awake, something vast, something that long ago stopped looking outward because it already found all the answers it needed. Dyson spheres have long captivated the imagination of storytellers, becoming a staple of science fiction where they often appear as symbols of ultimate technological achievement or hubris. Take Star Trek: The Next Generation, where the episode Relics introduced a massive, abandoned Dyson sphere discovered by the Enterprise crew. Visually stunning, this version was a perfect solid shell, so vast its interior surface could mimic an entire planetary ecosystem with its own weather patterns. But here's the twist: while undeniably cinematic, this design clashes with scientific reality. A rigid shell would crumple under gravitational stress, and the show hand-waved this with unobtainium materials, highlighting how fiction often prioritizes awe over physics. Then there's Larry Niven's Ringworld, a megastructure so iconic it reshaped sci-fi tropes. Though not a true Dyson sphere, its DNA is similar, a colossal ring encircling a star with a habitable inner surface. Niven's creation captured the scale and grandeur of stellar engineering, but even he later admitted the physics didn't quite hold. Ringworlds lack stabilizing thrusters to prevent orbital drift, a flaw fans dubbed the Ringworld instability. Yet these creative liberties matter less than the cultural impact. Ringworld popularized the idea that civilizations might reshape solar systems like clay, inspiring generations of writers and scientists to think bigger. Even video games have embraced the concept. Halo's titular rings, while weaponized, echo Dyson's vision of controlled stellar environments, and Stellaris lets players construct Dyson spheres as in-game projects, though the game gamifies the energy output, sidestepping the real-world heat dissipation nightmare. These portrayals, though simplified, serve a vital role. They make cosmic engineering feel tangible, even thrilling, to audiences who might never crack open a physics textbook. The cultural resonance of Dyson spheres reveals something deeper. They're more than plot devices, they're mirrors reflecting our hopes and anxieties about progress. When sci-fi depicts them as abandoned ruins freelancer or traps for unwary travelers, Doctor Who's The Impossible Planet, it whispers a cautionary tale. Mastery over stars doesn't guarantee survival. Conversely, when they're framed as utopian power sources, Sid Meier's Alpha Centauri, they embody humanity's boundless ambition. Perhaps the most intriguing fictional twist is the partial Dyson sphere, structures like the Alderson disk or Bishop ring, which embrace plausible engineering limits. These hybrids acknowledge the absurdity of a solid shell while keeping the dream alive. After all, sci-fi's job isn't to blueprint reality. It's to ignite wonder, to ask, what if? In ways that push real-world science forward, Freeman Dyson himself admitted his idea was partly inspired by sci-fi. The loop is poetic, fiction borrows from theory, then repays the debt by inspiring new generations to turn speculation into discovery. The takeaway: while Hollywood Dyson Spheres bend physics, their cultural footprint is rock solid. They've conditioned us to see stars not just as distant suns, but as raw material challenges waiting to be solved. And that shift in perspective might be their greatest gift to science. Every time a viewer gazes at a fictional megastructure and thinks, could we? The line between fantasy and future blurs just a little more. To grasp the sheer ambition behind a Dyson sphere, you need to understand the Kardashev scale, a cosmic ruler measuring a civilization's mastery over energy. Dreamed up by Soviet astronomer Nikolai Kardashev in 1964, this framework splits advanced societies into 3 tiers based on how much power they control. A Type I civilization harnesses all the energy available on its home planet. Think global fusion reactors, orbital solar arrays, and geothermal deep dives. We're not even there yet. By some estimates, humanity lingers around Type 0.7, but a Type Roman II civilization, that's where the scale bends reality. These are cultures capable of capturing every watt radiated by their star output measured in yottawatts, enough to power a galaxy-spanning empire. And that's precisely what a Dyson sphere represents, the ultimate energy infrastructure for a society that's outgrown planets. Consider the numbers. Our sun emits roughly 386 yottawatts per second. To put that in perspective, 1 yottawatt equals 1 septillion watts, a 1 followed by 24 zeros. Humanity's current global energy consumption, just 18 terawatts annually. A Type Roman II civilization would operate on a scale billions of times beyond that, channeling stellar fire into computation, propulsion, and maybe even realities we can't fathom. The energy demands alone explain why such a culture wouldn't just want a Dyson sphere, they'd need it. Growth requires resources, and stars are the universe's ultimate power plants. But energy isn't the only driver. The Kardashev scale hints at something deeper: survival. A species bound to a single planet lives on borrowed time. Asteroid strikes, supervolcanoes, or gamma-ray bursts could erase millennia of progress in an instant. By dispersing across a Dyson swarm or bubble, a civilization becomes virtually unkillable. No single disaster could wipe out all its habitats, and with a star's energy at its fingertips, it could weather cosmic storms that would doom lesser societies. This isn't just about power, it's about resilience, about ensuring that intelligence persists long after its homeworld fades to dust. Here's where the scale gets slippery. Kardashev originally framed Type Roman II as the pinnacle, but modern thinkers like Michio Kaku have expanded it. Type Roman III civilizations harness the energy of entire galaxies, using black holes or dark matter as fuel. Against that backdrop, Dyson spheres start to look quaint, mere stepping stones to greater feats. Yet even a Type Roman II society would seem godlike to us. Imagine beings who have rearranged solar systems like Lego bricks, who have stretched time itself by leveraging near light-speed travel powered by their star's output. Their art might be carved in plasma, their histories encoded in pulsar signals. The frightening part: if such civilizations exist, we might never recognize them. A mature Type Roman II culture could be so efficient that its waste heat, the very signal we're searching for, is minimized to near invisibility. Or perhaps they've moved beyond Dyson spheres entirely, tapping into zero-point energy or quantum vacuum fluctuations that leave no thermal trail. The Kardashev scale isn't just a measure of energy, it's a mirror showing how tiny we are in the cosmic dark. But it's also a challenge, a roadmap stretching from candle flames to starlight, whispering that the impossible might just be a matter of time. If a Dyson sphere represents the ultimate power plant, then a SETI thruster is the ultimate engine, a megastructure not just harvesting a star's energy but moving the star itself. Picture this: an enormous parabolic mirror positioned so that half the star's radiation reflects back onto its surface. The imbalance creates thrust, gently pushing the star and its entire planetary system through the galaxy like a cosmic sailboat. It's not fast. At best, a SETI thruster might accelerate a star to a few hundred kilometers per second over millions of years. But for a patient civilization, this could be a way to steer toward richer galactic neighborhoods or escape impending supernova. Unlike a Dyson sphere, which is all about energy, this is about mobility, taking your hometown with you on an interstellar road trip. Starlifting takes stellar engineering in a radically different direction. Instead of just using a star's energy, you'd mine it for raw materials. Stars are already vast reservoirs of hydrogen, helium, and heavier elements, but starlifting proposes actively extracting them. One method involves using intense magnetic fields to siphon off plasma from the star's surface, like tapping a cosmic maple tree. Another idea, deploying nanobots to skim material from the corona, processing it into usable elements mid-flight. The harvested fuel could power more megastructures, feed fusion reactors, or even construct new stars if a civilization gets ambitious enough. What makes these concepts fascinating is how they complement or compete with Dyson spheres. A SETI thruster might require leaving parts of the star's energy untapped to generate thrust, making it less efficient for pure power generation. Starlifting, meanwhile, could extend a star's lifespan by removing excess mass, but it might also destabilize it if done recklessly. Each approach reflects different priorities. Dyson spheres optimize for energy, SETI thrusters for navigation, and starlifting for resource extraction. Yet all three share a common theme. They treat stars not as distant points of light, but as raw material to be shaped. That shift in perspective is perhaps the most radical idea of all. Whether it's wrapping a star, pushing it, or mining it, these megastructures remind us that advanced civilizations might not just live in the universe. They might rewrite it. The universe might seem like a vast, empty stage waiting for civilizations to announce themselves, but what if the opposite is true? What if advanced societies aren't broadcasting their presence but hiding from it? This is the chilling premise of the dark forest theory, a cosmic game of hide and seek where the stakes are survival itself. The logic is brutal. In a universe teeming with life, any civilization revealing its location risks annihilation by rivals who see expansion as a zero-sum game. And that's where Dyson spheres enter the equation, not just as feats of engineering, but as potential bullseyes in the dark. Think of it like this. A Dyson sphere is the ultimate flare in the cosmic night, screaming, "Here we are." To anyone watching, its waste heat alone would glow in infrared across light years, a beacon that can't be dimmed. For a civilization adhering to dark forest logic, that's suicide. The theory suggests that any species building megastructures around stars might paint a target on their back, inviting preemptive strikes from neighbors who can't afford competition. After all, if resources are finite, why risk sharing when you could eliminate the threat first? But here's where it gets thorny. If the dark forest is real, wouldn't all advanced civilizations avoid megastructures entirely? Yet we keep scanning the skies for Dyson spheres, hoping to find them. This paradox hints at two unsettling possibilities. Either the theory is wrong, and spacefaring cultures don't see each other as threats, or we're missing something critical. Maybe Dyson spheres are out there, but their builders have found ways to cloak them, masking their heat signatures or disguising them as natural phenomena. Or perhaps the civilizations that build them don't survive long enough for us to notice. There's a darker twist. Some argue that a Dyson sphere could double as a weapon, a star-sized shield against aggression. Imagine repurposing those energy collectors into a directed energy arsenal, capable of vaporizing fleets or sterilizing planets. In a dark forest universe, power isn't just about growth, it's about deterrence. A civilization might wrap its star not just to thrive, but to warn, we can harness this fire, don't test us. Yet the most haunting question isn't whether Dyson spheres are dangerous. It's whether they're worth the risk. The dark forest assumes that survival means silence, but what if progress demands the opposite? A species might choose visibility because hiding forever means stagnation. No interstellar trade, no shared knowledge, no alliances. The same megastructure that makes you a target could also be your only path to transcendence. So as we search for cosmic megastructures, we're not just hunting for engineering marvels. We're probing the universe's deepest fears and its boldest hopes. Every flicker of infrared light could be a distress signal, a declaration of war, or an invitation. And until we know which, the dark forest looms, its shadows stretching across every star we dare to wrap. Building a Dyson sphere manually would take civilizations thousands of years, but what if the builders didn't have to lift a finger? Enter von Neumann machines, the ultimate cosmic workforce. These hypothetical self-replicating robots could revolutionize megastructure construction by turning raw asteroids into armies of builders. Picture a single probe landing on a metal-rich asteroid. It mines materials, constructs copies of itself, and sends those duplicates to new asteroids. Each new generation does the same, creating an exponentially growing swarm of robotic workers. Within decades, what started as one machine becomes billions, all tirelessly harvesting resources, fabricating solar collectors, and assembling them into a Dyson swarm without a single organic engineer in sight. The beauty of von Neumann machines lies in their efficiency. Unlike human-led projects constrained by lifespans and labor, these probes work on cosmic timescales. They don't sleep, don't tire, and most importantly, don't stop. A well-designed probe could adapt to different environments, processing ice for fuel, metals for structural components, and silicates for radiation shielding. Some theories even suggest they'd harness solar energy directly, using it to power their replication cycles far from their home star. This isn't just automation, it's evolution in steel and silicon, a leap from biology-driven industry to something entirely post-human. Of course, exponential growth comes with risks. A single programming error or mutation in the replication code could turn these machines into a cancer, consuming entire star systems in runaway expansion. Sci-fi nightmares like the Berserker probes or Grey Goo scenario warn of self-replicators gone rogue, wiping out planets as they multiply. But for a cautious civilization, safeguards might include built-in shutdown protocols or limiting replication to pre-approved zones. The rewards outweigh the risks. A von Neumann swarm could erect a Dyson sphere faster than any organic team, leaving its creators free to focus on higher pursuits or simply watch the stars bend to their will. The implications ripple outward. If von Neumann machines are possible, they might already be out there. Ancient probes could lurk in our asteroid belt, dormant or waiting for triggers we don't understand. Some scientists even propose that odd celestial objects, like the interstellar visitor Oumuamua, might be derelict machines from distant builders. Whether tools or threats, these replicators hint at a universe where the greatest structures aren't built by hands, but by the patient, tireless work of machines that outlast their makers. The materials needed to build a Dyson sphere don't exist, at least not yet. Steel, aluminum, even titanium would crumple under the heat, stress, and scale required. But what if the answer lies in the bizarre world of quantum physics and exotic matter? Imagine a material with the strength of diamond but the weight of a feather, or a superconductor that operates at stellar temperatures without failing. That's the kind of science fiction turned reality we'd need to make megastructures feasible. Take graphene, a single layer of carbon atoms arranged in a honeycomb lattice. It's 200 times stronger than steel, nearly transparent, and conducts electricity better than copper. On Earth, we struggle to produce it in large sheets, but a civilization mastering space manufacturing could grow it in zero gravity, free from the defects that plague terrestrial production. Now scale that up. Graphene-based solar collectors, ultra-light yet nearly indestructible, could form the backbone of a Dyson swarm. Even more tantalizing is graphene, a theoretical cousin of graphene with adjustable electronic properties. Custom-tuned graphene panels might absorb specific wavelengths of starlight with near-perfect efficiency, turning a star's fury into usable energy with minimal waste. Then there's metallic hydrogen, a form of hydrogen that behaves like a metal under extreme pressure. Predicted but not yet stabilized in labs, it could be the ultimate superconductor, channeling stellar energy without resistance. If harvested from gas giants or synthesized in orbital forges, metallic hydrogen might form the wiring of a Dyson sphere, linking collectors across millions of miles without energy lost. Even more radical, quantum dots, nanoscale crystals that manipulate light at the atomic level. Embedded in Dyson components, they could redirect or transform starlight on demand, turning the entire structure into a tunable energy filter. But materials are only half the battle. Quantum entanglement could solve the communication nightmare of a megastructure spanning solar system distances. Imagine entangled particles stationed across a Dyson swarm, allowing instantaneous data transfer between collectors. No lag, no signal degradation, just perfect synchronization, enabling real-time adjustments to orbits or energy distribution. Pair that with topological quantum computers managing the swarm's operations, and you've got a system so precise it could balance gravitational nudges from passing comets without breaking stride. The wildest possibilities lie in metamaterials, engineered substances with properties not found in nature. Photonic crystals could bend starlight around critical components, shielding them from heat. Self-healing alloys laced with nanobots might repair micrometeorite damage before it cascades into failure. And if room temperature superconductors ever move from theory to reality, they'd revolutionize energy storage, letting a Dyson sphere bank unimaginable reserves during peak output. Here's the catch: none of these materials are magic. Graphene tears under strain in ways we don't fully understand. Metallic hydrogen requires pressures rivaling a star's core. Quantum systems decohere at the slightest disturbance, but that's the point. Building a Dyson sphere isn't about today's tech. It's about what becomes possible when a civilization dedicates centuries to solving these puzzles. Every breakthrough in our labs hints at a future where the impossible is just engineering, and if another species out there already cracked these problems, their megastructures might shimmer with materials we've yet to name, forged in fires we've yet to light. The timeline for building a Dyson sphere isn't measured in years or decades. It's written in the ink of epochs, spanning durations so vast they reshape how we think about civilizations. For humanity, the path from our first mud huts to spacefaring explorers took roughly 12,000 years, but constructing a megastructure that encircles a star, that's a project stretching hundreds of millennia, maybe even millions of years. Consider our current energy output. If we sustain today's global construction pace, assembling a Dyson swarm would take longer than the existence of our species so far. But scale isn't static. With exponential advancements in robotics, AI, and space infrastructure, what once seemed impossible could accelerate dramatically if we survive long enough to make the attempt. Astrobiologists frame this conversation around the concept of cosmic deadlines. Stars like our Sun have finite lifespans, roughly 10 billion years, before they balloon into red giants and render inner planets uninhabitable. For an intelligent species, that's both a countdown and a motivator. If humanity lasts another 500,000 years, mastering asteroid mining and orbital manufacturing, we might lay the first Dyson swarm components. Another million years could see the swarm mature, capturing a meaningful fraction of solar energy. But here's the catch: civilizations face filters, catastrophes like climate collapse, nuclear war, or rogue AI that could halt progress entirely. The window to build might be narrow, even for a technologically adept species. Now shift perspective. What about older civilizations? The universe has been producing habitable planets for at least 9 billion years. If another intelligence arose just 1% earlier than us, a blink in cosmic time, they'd have a 100-million-year head start. For them, a Dyson sphere might already be ancient history, its collectors weathered by micrometeorites but still humming with energy. The Milky Way could be dotted with these relics, their builders long since moved on to technologies we can't yet imagine. Yet absence of evidence isn't evidence of absence. Some theories suggest that early civilizations might skip Dyson spheres entirely, leapfrogging to more exotic solutions like black hole energy extraction or dark matter reactors. Others propose that megastructures could be temporarily built for specific projects, then dismantled when their purpose fades. The time frame isn't just about physics, it's about psychology. How long does a culture retain the ambition to reshape stars before turning inward, preferring virtual realities or dormant hibernation? The answer might lie in cosmic archaeology. If we ever find a partially completed Dyson swarm, a star with irregular dimming and infrared spikes but no full enclosure, it could hint at a civilization that ran out of time, resources, or will. Or worse, a cautionary tale about the challenges of surviving long enough to harness a star's power. The timeline isn't just a countdown, it's a mirror reflecting the fragility and audacity of intelligence itself. For now, we watch the skies, knowing that every twinkle could mark a clock ticking, some much older than ours, others yet to start. Dismantling an entire planet sounds like the plot of a supervillain scheme, but for a civilization building a Dyson sphere, it might just be Tuesday. The ethical questions here aren't just philosophical, they're cosmic. Take Mercury, for example. It's rich in metals and close to the sun, making it prime real estate for mining in a future megastructure project. But what gives us the right to strip a world bare, even if it's barren by human standards? Planets, after all, aren't just raw materials. They're time capsules holding clues to how solar systems form and potential habitats for future generations or even undiscovered life. Crushing one into solar panels feels like burning a library to keep warm. And what about the star itself? Stars aren't static objects. They're dynamic, with magnetic fields, solar winds, and heliospheres that shape entire planetary systems. A Dyson sphere would fundamentally alter that balance. By capturing a star's energy output entirely, we'd be cutting off light and heat to any outer planets, potentially freezing worlds like Pluto into permanent deep space tombs. Even more unsettling, if multiple civilizations started building Dyson spheres, the collective dimming could change the thermal equilibrium of galaxies, subtly shifting the conditions for life across the cosmos. It's the ultimate tragedy of the commons. What happens when everyone wants a piece of the universe's pie? Then there's the question of unintended consequences. Imagine a Dyson Swarms orbit destabilizing over millennia, its millions of satellites drifting into chaotic collisions, creating a deadly debris field. Or worse, a malfunction turning the swarm into a star-shrouding weapon, blocking light to dependent ecosystems. We've seen how fragile Earth's climate is now. Picture that on a galactic scale. The sheer permanence of these megastructures raises another moral quandary. Once built, could they ever be undone? Future civilizations might inherit a sky full of engineering relics, their stars shackled by choices made centuries earlier. But here's the counter-argument: survival might demand sacrifice. If humanity stays planet-bound, we risk extinction from asteroid strikes, supervolcanoes, or our own self-destruction. A Dyson sphere could be the ultimate insurance policy, scattering our presence across a swarm of habitats too numerous to wipe out. From this perspective, dismantling Mercury isn't vandalism, it's evolution. After all, nature isn't sentimental. Stars already devour planets during their death throes. If intelligence is rare in the universe, does preserving it justify reshaping a few lifeless rocks? The debate echoes terrestrial ethics on steroids. Is it okay to mine the moon if it means saving Earth's ecosystems? Should we prioritize potential alien microbes over human expansion? These aren't just hypotheticals, they're dress rehearsals for the kind of choices a spacefaring civilization must face. And perhaps the most humbling thought of all, if other species have already built Dyson spheres, their silence might be an answer in itself. Maybe the great filter isn't about technology, but wisdom. The universe could be littered with the ruins of civilizations that mastered star harvesting, but forgot to ask whether they should. A Dyson sphere isn't just a power plant. It could be the universe's most powerful signal flare, broadcasting a civilization's presence across the galaxy without a single radio transmission. Imagine a star that flickers not from natural processes but by design. By strategically adjusting the arrangement of its energy collectors, an advanced civilization could create deliberate patterns in the star's light pulses, dimming sequences, or even binary messages visible from thousands of light years away. Unlike fleeting radio signals that dissipate into cosmic noise, these optical beacons would persist for epochs, etched into the very fabric of a star's luminosity. It's the ultimate shout into the void, "We are here," but the communication potential goes far beyond simple greetings. A Dyson swarm orbiting at varying distances could modulate a star's output like a colossal dimmer switch, encoding vast libraries of information in its flickers. Picture this: collectors shifting position to create pulses lasting decades slow, deliberate flashes spelling out mathematical constants or biological blueprints for any observing civilization to decode. The star itself becomes the medium, its light a carrier wave for knowledge spanning millennia. This isn't just messaging, it's cosmic cryptography on a scale that dwarfs human language. There's another possibility: unintentional signals. Even a fully operational Dyson sphere optimized for energy would leak clues. Waste heat, structural imperfections, or collector movements might imprint statistical anomalies in infrared emissions. To a distant observer, these irregularities could form a distinctive signature, like finding Morse code in the static of a star's thermal glow. The very act of building megastructures might leave forensic traces, revealing a civilization's technological fingerprints whether they intended to communicate or not. The implications for interstellar diplomacy are profound. A species that deliberately modulates its star's light is signaling not just its existence but its confidence. Unlike radio broadcasts that risk attracting hostile attention, a Dyson beacon implies capability. The sender controls stellar-scale engineering and isn't afraid to show it. Conversely, detecting accidental leakage from someone else's megastructure would be like stumbling upon ruins in a forest. The builders might be long gone, their messages echoing into eternity without reply. Yet here's the catch: not all communication is deliberate. Advanced civilizations might repurpose Dyson components for entirely different goals, like propulsion. Imagine a SETI thruster nudging a star toward another system, its infrared plume forming an unintended wake detectable across light years. Or consider waste heat funneled into laser arrays for interstellar travel, creating temporary but brilliant flashes visible to telescopes. Even a society hiding under dark forest logic might leave traces through the sheer physics of their engineering. This duality, intentional and unintentional, signal and artifact, redefines how we search for intelligence. Traditional SETI scans for radio waves, but Dyson spheres suggest we should also monitor stars for engineering signatures, unusual thermal profiles, asymmetric dimming, or rhythmic oscillations that defy natural astrophysics. The universe's greatest conversation might not be in languages or lasers, but in the silent, patient architecture of starlight itself. And if we ever decode those patterns, the message won't just be hello, it'll be a mirror showing us how far we still have to go. Imagine a Dyson sphere buckling under the star's gravity, its colossal plates warping like tin foil in a furnace. The first sign of trouble might be subtle: a tremor in the orbital harmonics, a stress fracture propagating through a support beam. But once the cascade begins, there's no stopping it. A single failing component could trigger a domino effect, sending trillions of tons of infrastructure spiraling inward. The star's gravity would shred the collapsing shell into fragments, superheating the debris into plasma as it plunges into the stellar atmosphere. For any civilization living on the sphere's interior, it would be like standing on the roof of a skyscraper as the supports vanish beneath you. Except the skyscraper wraps an entire star, and its collapse rains white-hot shrapnel at relativistic speeds. Thermal runaway paints an even grimmer picture. A miscalculation in heat dissipation could turn a Dyson sphere into a cosmic pressure cooker. As temperatures rise, materials expand, warp, and lose structural integrity. Cooling systems overload, and soon the entire megastructure begins to glow, not with harnessed energy, but with waste heat spiraling out of control. The interior becomes an oven, baking habitats and machinery alike. Survivors would face an impossible choice: flee into the void with limited resources, or suffocate as life support systems fail under the relentless thermal onslaught. And if the sphere's orbit decays, the entire structure could plunge into the star, its remains vaporized in a final, furious eruption of light, a monument to ambition turned to ash. Then there's the silent killer: orbital instability. A Dyson swarm relies on perfect coordination, each component meticulously balanced against gravitational forces. But introduce a rogue element, a stray black hole passing through the system, a warped space-time ripple from a distant supernova, and that delicate dance unravels. Collectors collide, their debris fields spawning cascading impacts. What began as a symphony of precision becomes a cacophony of destruction, with shrapnel carving through neighboring satellites at thousands of kilometers per second. The swarm's AI fails to compensate, its repair drones overwhelmed by the scale of disintegration. Within centuries, the star's once pristine orbit becomes a graveyard of tangled wreckage, its energy output lost to the chaos. The most chilling possibility: sabotage. In a universe where civilizations compete for resources, a Dyson sphere isn't just a power source, it's a strategic vulnerability. A single well-placed attack, whether kinetic bombardment or a nanotech virus corrupting control systems, could doom billions. Imagine a rival species hacking the swarm's navigation protocols, redirecting collectors into fatal collisions. Or worse, weaponizing the sphere itself, focusing its captured starlight into a beam capable of sterilizing planets. The very infrastructure designed to elevate a civilization could become the instrument of its annihilation. Yet these catastrophes aren't just warnings, they're puzzles waiting for solutions. Could future engineers design fail-safes, like emergency jettison systems for overheating segments? Or decentralized swarms resilient to single-point failures? The ruins of dead civilizations might hold the answers. If we ever find a star surrounded by strange debris, twisted metal in unnatural orbits, or infrared ghosts of melted megastructures, it could be a tutorial written in starlight. This is how not to build a Dyson sphere. The universe doesn't forgive engineering arrogance, but for those who learn its lessons, the stars might just yield their power without tragedy. Black holes might seem like the last place you'd want to build a megastructure: cosmic vacuums that devour light itself. But for an advanced civilization, they could be the ultimate power source, dwarfing even the energy output of stars. Picture this: instead of wrapping a sun, engineers construct a Dyson sphere around a black hole, tapping into the ferocious forces at its edge. It sounds like science fiction, but the physics checks out, with consequences that bend the imagination. First, consider the accretion disk, a swirling maelstrom of superheated gas and dust spiraling into the black hole at nearly light speed. The friction here generates temperatures in the millions of degrees, unleashing X-rays and gamma rays with energy outputs that make our sun look like a candle. A Dyson-like structure here wouldn't just capture visible light, it'd harness this high-energy fury, converting it into usable power on scales that defy belief. Some calculations suggest the energy from a single active galactic nucleus could power a civilization for billions of years. But what if the black hole is quiet, its accretion disk faint or absent? Enter Hawking radiation, the faint glow of particles escaping a black hole's gravitational grip due to quantum effects near the event horizon. For stellar mass black holes, this emission is minuscule, barely a whisper above absolute zero. But scale matters. Smaller black holes emit more Hawking radiation, and an artificial black hole, say one crafted to weigh just a few trillion tons, could radiate at thousands of degrees, turning into a hyper-efficient power plant. A civilization might feed it stray asteroids to maintain mass, balancing evaporation with intake to sustain the perfect energy output. The engineering challenges, of course, are monstrous. Time dilation near the event horizon means construction crews would experience time differently. A worker close to the black hole might age minutes while centuries pass elsewhere. And then there's the radiation. Without shielding beyond anything we can currently conceive, the intense X-rays and gamma rays would fry any normal material. Exotic solutions might include force fields or quantum-locked barriers, technologies that sound like magic today but could be routine for a species that's mastered black hole physics. Yet the payoff could redefine existence. A black hole Dyson sphere wouldn't just provide energy, it could serve as a time capsule, a supercomputer, or even a propulsion system. Imagine using the black hole's gravitational slingshot to hurl entire star systems across galaxies, or encoding data in Hawking radiation pulses to send messages billions of years into the future. The very laws of physics that make black holes terrifying also make them versatile tools for a civilization thinking in cosmic timeframes. Here's the kicker: if other civilizations have already gone this route, their black hole megastructures might be invisible to our telescopes. A perfectly efficient system would leave no waste heat to detect, hiding in plain sight. The only clue might be unnatural gaps in the expected locations of black holes' holes in the universe's fabric where something or someone has already staked a claim. The hunt for Dyson spheres around stars might just be the beginning. The real masterpieces could be lurking where the light ends. Reports of unidentified aerial phenomena UAP have surged into mainstream discussion. But what if some of these mysterious objects aren't just visiting Earth? What if they're autonomous probes from civilizations that have already mastered Dyson spheres? It's a fringe theory that pushes the boundaries of credibility, yet it raises a provocative question. If an advanced species can encircle a star, wouldn't they also develop the means to explore the galaxy? Consider the logistics. A civilization capable of building a Dyson sphere would possess energy reserves beyond comprehension, enough to power self-replicating probes for millennia. These machines, sometimes called von Neumann probes, could spread across the Milky Way like cosmic dandelion seeds, scouting for resources, habitable worlds, or even other intelligence. Their propulsion systems might harness beamed energy from their home star or tap into exotic physics we've yet to discover, explaining the sudden accelerations and maneuvers reported in UAP encounters. And if these probes are millions of years old, their technology would appear godlike to us, as incomprehensible as a smartphone to a caveman. Skeptics, of course, dismiss this as wishful thinking. UAPs often have mundane explanations: atmospheric anomalies, classified military tech, or sensor glitches. Even the most baffling cases lack the unambiguous evidence needed to tie them to alien megastructures. But the scientific method demands we follow the data, not just our hopes. If a UAP exhibited propulsion defying known physics while emitting infrared signatures matching theoretical Dyson probe designs, that would be a game changer. So far, no such smoking gun exists, yet the absence of proof isn't proof of absence. Some theorists suggest these probes might be dormant, hibernating in our solar system's outskirts until triggered by our radio signals, nuclear tests, or space exploration. Others propose they're stealthy by design, avoiding detection to prevent cultural contamination or panic. The truth could be even stranger. What we perceive as craft might not be physical objects at all, but projections or drones operating at scales imperceptible to human senses. The real test lies in our ability to scrutinize these phenomena without flinching from either wild speculation or rigid skepticism. As we expand our search for Dyson spheres in distant star systems, we might find clues closer to home, hidden not in the stars, but in the unresolved mysteries buzzing through our own skies. Whether UAPs are secret tech, cosmic debris, or something far beyond our understanding, their persistence in human lore suggests one thing: the universe is stranger than we're willing to admit. And sometimes the most extraordinary answers lurk in the gaps of our ignorance. The search for Dyson spheres is entering a golden age, thanks to a new generation of telescopes and the power of crowdsourced discovery. Leading the charge is NASA's James Webb Space Telescope, a marvel of engineering capable of peering deeper into the infrared spectrum than any instrument before it. While Webb wasn't specifically designed to hunt megastructures, its unprecedented sensitivity makes it ideal for spotting the thermal fingerprints of stellar-scale engineering. Imagine analyzing a star's light curve and detecting not just the gentle dip of a passing planet, but the irregular, jagged shadows of colossal energy collectors, or catching the faint infrared glow of waste heat where none should exist. Webb's early observations have already upended our understanding of distant star systems, and as it continues scanning the cosmos, the odds of stumbling upon something truly unnatural grow stronger every day. But Webb is just the beginning. The proposed Louvois telescope, a behemoth with a mirror up to 15 meters wide, could revolutionize the hunt. Designed to directly image exoplanets, Louvois' spectral resolution would let scientists dissect starlight with forensic precision, identifying chemical signatures that betray artificial origins. Picture this: a star's light shows traces of exotic alloys or industrial pollutants, hinting at orbiting megastructures built from materials not found in nature. Louvois might even spot the reflected glare of unfinished Dyson Swarms, their half-built components glinting like cosmic construction sites. If funded, this telescope could launch by the 2040, turning speculative theories into testable science. Yet the future of Dyson sphere research isn't just in the hands of billion-dollar observatories. Citizen science initiatives like Planet Hunters are democratizing the search, empowering amateur astronomers to sift through telescope data for anomalies. It was volunteers who first flagged Tabby stars' bizarre dimming, proving that the collective curiosity of thousands can rival professional expertise. Now, platforms like Zooniverse are training AI to assist in the hunt, combing through petabytes of data for stars that behave wrong. The next breakthrough might come not from a lab, but from a high school teacher in Oslo or a retired engineer in Buenos Aires, staring at their laptop and realizing, this flicker isn't supposed to happen. The real game changer, though, could be data synthesis. Modern algorithms are learning to cross-reference infrared surveys with optical observations, gravitational wave detections, even neutrino fluxes, searching for correlations that scream artificial. Imagine a machine learning model flagging a star that's unusually dim in visible light but emits a precise pattern of neutrinos, a signature consistent with a contained fusion reactor at its core. Or spotting gravitational lensing distortions that suggest an invisible megastructure-scale mass-bending spacetime. The tools to find these needles in the cosmic haystack are arriving faster than we anticipated. What's thrilling isn't just the technology, but the philosophical shift it represents. For decades, the search for extraterrestrial intelligence focused on radio signals, an approach rooted in 20th century communication. But Dyson sphere research acknowledges a deeper truth. Advanced civilizations might not talk like us, but they'll inevitably leave thermodynamic traces. Waste heat, orbital mechanics, material science, these are universal constraints that even the most alien engineers must obey. Whether we find megastructures in 10 years or 10 centuries, the hunt itself reshapes how we see our place in the universe. Every star becomes a question, every anomaly a potential door, and behind one of them something or someone might be waiting. From the visionary scribbles of Freeman Dyson to the cutting-edge telescopes scanning for infrared anomalies, we've journeyed through the mind-bending possibilities of cosmic megastructures. We've seen how a Dyson sphere isn't just a shell around a star. It's the ultimate power grid for civilizations playing with stellar fire, whether as a swarm of elegant collectors, a precarious solid shell, or even a black hole's deadly embrace. We've explored the physics that makes them plausible, the mind-numbing engineering challenges that render them nearly impossible, and the eerie stellar oddities like Tabby's star that keep astronomers whispering about alien architects. But the most thrilling questions linger. If these titanic structures exist, who built them? Are they the work of thriving societies radiating godlike mastery, or the crumbling tombstones of species that reached too far? The silence of the cosmos might not mean we're alone. It could mean we're not listening for the right clues. Waste heat, irregular starlight, the ghostly imprint of quantum-entangled megastructures, every anomaly is a potential message waiting for us to decode it. And now, the final puzzle. If we ever unambiguously detected a Dyson sphere hanging in the void, its star dimmed by design, what then? Would we dare reach out, knowing the builders could be millions of years ahead of us? Or worse, long extinct, leaving only their stellar machinery humming in the dark? The answer isn't just about science, it's about courage. Do we shout into the cosmic forest, or do we hold our breath, mindful of the shadows between the trees? The universe doesn't owe us answers, but it does offer mysteries, and that's where you come in. What do you think? Are Dyson spheres out there hiding in plain sight? And if we found one, would you hit reply? Drop your thoughts below and don't forget to subscribe. The cosmos has more secrets to share and we're just getting started.